we have in the emitter leg, we have the emitter resistance as Re, and we are applying the voltage source over here as VEE, right? And we are taking the output from the emitter of the transistor via capacitor C2. And the base is being connected to, the collector is being connected to the ground. Now, if you can see in the circuit, we have the input that is being applied to the base of the transistor. We are taking the output from the emitter of the transistor. So this means this circuit is behaving as a common collector configuration circuit. This means the collector is common in between the input side as well as the output side. Now, as we are doing the DC analysis of the circuit, so what we are going to do, we are going to make it a DC circuit. And for making it a DC circuit, this means we are going to take the input capacitor as well as the output capacitor out from the circuit. And when we are going to take that, this means we are left with a circuit that is something like this, right? So now this is the modified circuit which we have and which we are going to analyze it for the input side as well as for the output side. Now, if you can see, we have the base current which is flowing in the base of the circuit, and the base current will be IB. There is a current which is flowing in the emitter of the circuit, that will be IE. And from here, we can analyze the input side as well as the output side of the circuit. And if you see at the base emitter junction, we have the voltage which is VBE, and at the collector and emitter we have the voltage which is VCE, right? Are you with me?
Yes, sir.
Any question up to now?
No, sir.
So what we can do, we can analyze this circuit, and when we analyze this circuit, so we can have the input side. This will be the input side, and when we analyze the circuit, so we can apply KVL. KVL can be applied like this. So applying the KVL to this loop, what we are going to get, we will have the equation that will be, actually we can say, let's see before going further on. So this means we have a drop across the base resistance RB. Then we will have a drop from base to emitter BBE. Then we will have a drop in the emitter resistance, that is IERE, and that should be equal to the potential or the bias which is being applied to the emitter leg VEE, right? So this means we can write the equation applying KVL. KVL to input, and KVL to the input will be equal to, we can say, VEE is equal to IB RB plus VBE plus IE RE. Are you with me?
Yes, sir.
Yes.
Okay, ji. So, and we also know this thing that IE is equal to beta plus 1 times IB. So, by inserting this value against IE in this equation above, we can write VEE is equal to VBE plus IB RB plus beta plus 1 times RE. Are you with me?
Yes, sir.
Right? Or we can say IB can be written as VEE minus VBE divided by RB plus beta plus 1 times RE. Are you with me?
सर हम आपके साथ होते हैं पर लिखते हैं माइक पहले ऑफ किया होता है तो हम हर दफा नहीं कह सकते.
अच्छा ठीक है जी. Because
yes, sir. तो
I want to know that if you are following it or not, right? So that
नहीं
is
सर हमें अगर ये सर वो आपकी बात ठीक है लेकिन हमें अगर प्रॉब्लम हो हम पे सीधा कहेंगे कि सर नहीं.
चलें ठीक है बस. Then I will go ahead, right?
Yes,
Okay.
sir.
Okay. So this is the base current which we have figured out from this circuit, and when we try to analyze the output side, so
सर जी सर जी अगर ये आई बी क्यू फाइंड करना हो हमने ना क्यू पॉइंट पर ना तो फिर इसके लिए क्या फार्मूला होगा अगर बीटा की वैल्यू गिवन हो.
जी यही तो ये जो हमने वैल्यू निकाली है ये बेसिकली IBQ के लिए ही है. ठीक है जी. Because this will be indicating that specific point of the base current which will be providing us the collector current, right? And in that specific case it will be basically the IE current, right? Because IE will be at the output characteristic curve will be in between IE and VCE, because this is the emitter follower circuit. Are you with me?
Yes, sir.
ठीक है जी. So when we take a look of the output side, so in the output side we have the circuit is this. Circuit is this. So applying KVL to the output side, and when we apply the KVL to the output side, what we are going to get, the equation will be KVL to the output loop or output side. We will have the equation that will be VEE will be equal to VCE plus IE RE. Right? Are you with me?
Yes.
Yes, sir.
Yes.
And similarly, we can say VCE is equal to VEE minus IE RE, right? And if you see this, we can find from here VCEQ and IEQ, right? So this is basically the point from where we are actually having the Q points in the characteristic curve as well as on the load line, right? Are you with me?
Yes, sir.
Yes, sir.
ठीक है जी, rest of the thing is the same. Okay, so with this you can actually go through the example number 4.16, right? So go through the example number 4.16, and that is actually revealing the same circuit with the values inside it. Okay ji. So the next circuit which we are going to take a look is the common base configuration circuit.
सर
Common
यहाँ पर व्यू इंक्लूड करें
जी,
आप बताइए असाइनमेंट
zupoina shum tasawe.
सर एग्जांपल 4.16 पार्ट इंक्लूड
Da us नवे assignment तासु त नन मिलावी गया ये के बदा इंक्लूड कीगी, ठीक छो?
यस सर
Oh. Okay, the next circuit is common base configuration circuit. Okay, as the name indicates, it is common base. So this means the base is basically common in between the input side and the output side. Okay, the circuit which we have is basically we have the emitter resistance RE, and with that we have the biasing voltage, and similarly on the collector side we have the collector resistance, and we have the other biasing voltage, which is over here we say it is VCC, and over here we say it is VEE, right? And with that the base is grounded. With that we have the input which is being applied via C1, and the output is being taken from the collector side via C2, right? Now as we know that we are doing the DC analysis up to now, so this means what we can do, we can take out C1 and C2 from the circuit so that the circuit should become the circuit which is good for the DC analysis of the common base configuration circuit. Now if we try to label it, so it will be the currents, the current which is flowing in the collector is IC, the current which is flowing in the base is IB, and the current which is flowing in the emitter leg will be IE, right? Now we have the input side, and in the input side what we have this, if I just try to encircle the input side. So this is the input side of this common base configuration circuit, and what we can do, we can apply KVL to the input side. Applying KVL to the input side, we also have over here is the drop between the base emitter, which is VB, right? Now when we apply this, what we are going to get, let's see. So we can say VEE is equal to IE RE plus VBE, right? And what we can say that IERE should be equal to VEE minus VBE, or this means I can write IE is equal to VEE minus VBE divided by RE, right?
Yes, sir.
Now if I apply, so from here we can find the value of IE. Now if I apply to the same circuit, and if you see we have an outer loop in the circuit as well. So the outer loop can be we can have the outer loop which is going like this. Are you getting it? This is the outer loop of the circuit which I have marked it.
No.
No, sir.
The outer loop, because what we are saying up till now, we have the input side and we have the output side, but over here we can also take a look, and this can also become a loop which we call it as an outer loop. So in the outer loop what we have actually, if you see what I have marked it, that we have basically the potential across the collector emitter junction as VCE. Also I have a drop in the emitter lag as IERE. Then I have the biasing source VEE. Then I move across, and then I go, and then I have the biasing source VCC, and then I have the drop across the collector resistance, which is RC. Are you getting it now?
Yes, sir.
The one which I have marked it with a different color, right? So let me repeat it again. The outer loop is we have the drop across the collector emitter junction. Then I have a drop across the emitter resistance RE. Then I have a biasing source VEE. Then moving across and going to the other side is the biasing source VCC. Then I have a drop across the collector resistance RC, right? So if applying the KVL to this outer loop, what we are going to get, let's see. Right, applying KVL to the outer loop, KVL to outer, KVL to outer loop, right? So applying KVL to the outer loop, what we are going to have, we will have a drop across the RC as well as we have the drop across RE, right? Now in RC the current which is flowing is IC, and in RE the current which is flowing is IE. But as we know, the IC is actually equal to IE, right? So what we can say that, as well as if you see the two biasing sources, they are, when you are moving in the loop, they are reinforcing one another, right? So when you are moving in the loop, so we have always the voltage rise of the two biasing source, because when you are moving in the loop, if you see the direction of the loop which I have marked it, so in that direction the voltages VEE and voltage VCC, they are actually reinforcing one another. This means they will be coming up in the addition of one another, right? So when I write the equation, so it will be, let's see, it will be, I will write VEE plus VCC is equal to the drop across the emitter resistance IERE plus the drop across the collector emitter junction which is VCE, and plus I have the drop in the collector leg which is ICRC, right? Are you with me?
Yes, sir.
Yes, sir.
Repeat करें
Okay.
equation repeat करें
Equation, okay. If you see, if I go back to the circuit, let's see the circuit again. So if you see the both the DC biasing sources VEE and VCC, when you are moving in the loop, both they are reinforcing one another, right? So when they are reinforcing one another, this means they are in addition to one another. And then
reinforce
it,
क्या
J,
reinforce का क्या मतलब सर
रीइंफोर्स का ये मतलब है कि अगर आप ए को बी के साथ ऐड करते हैं, दिस इज रीइंफोर्सिंग. अगर ए की वैल्यू 5 है, बी की वैल्यू 10 है, व्हेन यू ऐड द टू, सो दे रीइंफोर्स एंड द सम विल बी 15, right?
yes sir yes
So what I am saying, the two biasing sources, they are actually adding up, right? So for use simplification, adding up, and then if you see there is a drop in the emitter leg which is IERE, plus
yes
there is drop across the collector emitter junction which is VCE, and then there is a drop across the collector leg which is ICRC, right? And then if you see, we have we know that IE is approximately equal to IC. So what we can say, that we can replace IC by IE in the equation, and once we replace it, we can write VEE plus VCC is equal to VCE plus IE RE plus RC, right? Or I can say VCE is equal to VEE plus VCC minus IE into RE plus RC, right? Now, if I apply the KVL to the outer loop, and the outer loop over here can be identified as, let's suppose I say the outer loop is this one is now the outer loop, right? Can you see it? Which I have marked. And applying KVL to the outer loop. So what we have something more over here, which is the drop in between the collector and the base junction, which is VCB over here, right? So applying KVL to this, what we are,
सर दोनों लूप का एक नेम होगा, उससे पहले जो बड़ा लूप है उसका भी लूप नाम है उसका भी.
okay, जो previous loop था, we have called it outer loop, and this is basically the output side, right?
Yes sir.
Right, if you see to this KVL to the outer loop I have written, right? And now this loop is basically the output side, KVL to the output side, right? So if I apply KVL to the output side, KVL to the output side, what we are going to get, we can simply write VCC is equal to the drop across the collector resistance plus the drop in the collector base junction, right? Or what I can say, VCB is equal to VCC minus IC RC. But as we know, IE is almost equal to IC, and so we can replace IC over here by IE. So we can write this, that it can be replacing this IC by IE. So this can be VCB is equal to VCC minus IE RC, because we have already figured out the value of IE from the first equation which we have done for the input side, right? So once we have done this, we can use it in the rest of the equations, and therefore we are converting these values into IE specific, right? So with this, what we can do, we can actually figure it out, the different circuits. And with this, there is an example 4.17. So this will be also included in the assignment, which you are going to get it today. Okay, there is also another assignment with miscellaneous bias configurations in the book. So there is an example 4.18 and there is an example 4.19, and there is, okay, there is an interesting example, example 4.20. Okay, let's see that example. I will just give you the overview of that because it is something different. So therefore I am giving you the idea. Okay, in the book, it is being given in example 4.20. If I have the book which is open, so I can show you. Okay, can you see it?
Yes, sir.
The example 4.20. So in this, as you can see, there is a voltage divider circuit which is being given, but there are two biasing sources which are being installed in the circuit. There is one which is VCC, and then there is another one VEE, right? Can you see it?
Yes,
Yes,
sir.
sir.
So there are two biasing sources which are being installed in the circuit, and then as you know, the voltage divider bias configuration circuit can be solved by two methods. One is the exact method, the other one is the approximate method. So if we are supposed to solve this with the exact method, so what we need to do, we need to actually go and find out the Thevenin equivalent voltage and the Thevenin equivalent current for the circuit, right? Do you remember that, which we have done last time,
Yes, sir.
Yes, sir.
right? So in that specific case, what we are supposed to do, we are going to have the Thevenin equivalent of this circuit, and the Thevenin equivalent of this circuit will be, we are going to figure it out, the Thevenin equivalent resistance, right? So this means the R1 and R2 will become in parallel. Can you see figure 4.56, right?
Yes, sir.
Right. So taking a look of figure 4.56, we can see that R1 and R2, they become in parallel, and when they become in parallel, so we can find the Thevenin equivalent resistance, which is RTH, right? Are you with me?
Yes, sir.
Yes, sir.
Right? And similarly, we need to find the Thevenin equivalent voltage, which is ETH, right? So if you see, the ETH will be figured out from base to the ground. The figure 4.57. Are you with me?
Yes, sir.
Right? So how we can go ahead with that? So if you see, we are putting back the voltage sources back in the circuit, and we will be trying to figure it out what is going to be the value of current which is flowing in this combination circuit, right? So how we can find the value of current? Again, it is simple, that we can apply KVL to the loop, which is from VCC, R1, R2 and VEE, right? So if we apply the KVL to this loop, so what we are going to get, let's see. So applying KVL to this loop, we will have something, right? So applying KVL to this loop, what we are going to get, if you see, we have this equation which is coming up. I is equal to VCC divide VCC plus VEE divided by R1 plus R2. Are you with me?
Yes, sir.
या समझ नहीं आ रही?
आगे आगे sir.
Let me just go back and I'll show you what is happening over here, right? So if you see the circuit, so in the circuit we have, if you see VCC, then the drop across R1, then the drop across R2, and then VEE, right? So if I go back, so what we have VEE